Good morning, Rogers County. Welcome back to another episode of Science with Kehler. I am Stephanie Kehler. I teach science here at Sequoyah Mid-High High School. I teach 9th grade physical science and upperclassmen zoology. Today I thought I would do a physical science lesson. Ironically, it is also Newton's laws. I'm going to have to get together with Mr. Harshfield, make sure we don't duplicate. But the good thing is we have some different demonstrations, and it's just another way to look at it. I always tell students, when you are trying to learn a concept, talk to multiple people if you're having a hard time. I used to kick my kids next door to the science teacher. If they weren't getting what I was explaining about mitosis, maybe the next teacher might explain a little bit differently, and it clicks. So what I'm going to do is talk about Newton's laws. I'm going to have some people helping me out from around Rogers County, and we're going to look at some of the different things that go on. So with Newton's laws, you already know that it's Newton's laws of motion, okay? And so we're going to go through all three of the laws and talk about why this was such a fun thing to have a couple years ago. I still enjoy them. They were the bane of most teachers' existence. I think we took a lot of these, and that's probably how I got this one. But Newton's laws of motions. Newton's first law is going to talk about how things are moving or how things are not moving. So the first video I have for you today, Maddie gave me when we were still back in school. I actually did Newton's 3 laws with my students, and they had to develop videos that showed me they understood the concepts. And so this is Maddie's video from class, and I'm going to try and expand. Oh, can I go back? Yes, right there. Go back. All right. And we're going to play this video, and if you can expand it, Miss Bacon.
Go.
Okay, what happened? Maddie's little brother helped out, which was awesome, and he hopefully learned some things here as well. What did you notice? Let's try it again.
Go.
Okay, on go. What does he do? He pulls that piece of paper out, and his tower of cups remains where they are. Okay, we're going to put all that into talking about motion. What is in motion? The paper. What's not in motion? The cups. Okay, so what we have here is Newton's first law stated one way. There's two different ways to state it. The first one says objects do not change motion unless acted on by an unbalanced force. There's a lot of vocabulary in there. Okay, so the first thing I want to talk about is the word objects. In my class, students are not allowed to use the word things or stuff. So the word objects is a good way to get around that. It's anything that has mass. Let's talk about mass. It has matter inside of it. So it could be air, it can be a solid, it can be a liquid. So an object doesn't want to change motion. So if you're already in motion, you want to continue in motion. Yes, sir?
How is mass measured?
Mass is going to be measured kind of like weight on the planet Earth. We're going to measure it in pounds or kilograms. So what I usually do is give my students a triple beam balance and ask them to find the mass of different objects. But it is a little bit different than weight because weight is a mass that is affected by gravity. So when I'm here on planet Earth, my mass is the same as on the moon. However, when I go to the moon, my weight will change because there's less gravitational pull. So it's a good place to hang out if I want to feel good about myself. All right, so the objects are not going to change motion unless they're acted on by an unbalanced force. Okay, unbalanced and force are the two other terms I want to talk about really quickly. When we talk about something being unbalanced, it's unequal. Okay, so whenever I think of unbalanced, I always think of a seesaw. If you have it unbalanced, it's going to have a high and a low. So when we're talking about an unbalanced force, that means there has to be more force or less force involved in the scenario, whatever it is. Force is literally just a push or a pull. That is the greatest definition. My kids love to write that one down because it's an easy one to remember, a push or a pull. So if I want to have an unbalanced force, I want to have more push or more pull, or less. Okay, I can decrease it, but either way, it's an unbalanced force. So if I have it in motion, it's just spinning. It's not going to change its motion unless I stop it because I created an unbalanced force for it. Okay, so here we have another word to describe Newton's first law. It's called inertia, and we're going to talk about inertia here in just a second, but here's some examples of the law. Another way to explain the law is to say An object in motion stays in motion. And so what I did was I asked some students from around Rogers County to help me demonstrate objects in motion stay in motion. So this is my friend Brantley, and Brantley's going to show you an object in motion stays in motion. I'm not sure you'll be able to hear the video, and I just want to explain to you quickly. He has a remote control car here, and what's kind of hard to see is that there's two eggs there. One gets a seat belt, and the other one does not. But Brantley is going to show you an object in motion stays in motion.
Objects in motion stays in motion. Here we go.
Whoa. Okay. I love Brantley. He's such a great kid. So what had happened in this case, the object in motion stayed in motion unless an unbalanced force acted on it. So my remote control car stays in motion until it gets to the wood blocks, the wall. It stops its motion. That wood block is an unbalanced force because it made it stop. However, the egg wants to continue in that forward motion. So we'll watch one more time. His seatbeltless egg.
Objects in motion stays in motion. Here we go.
Okay, so we can also look at this and compare it to real life. If you have a fast driver in your family and all of a sudden something has them stop, okay, they're in a car and we need to quickly stop, what do you notice in the car? If you're wearing your seatbelt, you're this egg right here, and it pushes on it. The unbalanced force is now my seatbelt protecting me and keeping me where I belong, but you can feel the inertia continuing in the same direction. If you're not wearing your seatbelt and you're in the back seat, you probably just hit your head on the front seat. So that would be egg number one over here. It continues in that motion. The object in motion stays in motion. The second part, sorry. No, I want to skip to the next slide. The second part of an object in motion stays in motion is an object at rest stays at rest. All right, so in the beginning it just said they want to continue doing what they're doing. This is another way of wording it, and most students are more familiar with it this way. So Miss Whitney is going to show us an object at rest stays at rest.
And I'm in kindergarten, and my teacher's name is Miss Rosanna. Object at rest stays at rest. Now we're going to pulleys. See, they all fall on each other, and let's see if they do.
That was awesome. Thank you. You're welcome. Thank you, Miss Whitney. That was awesome. So she shows an object at rest stays at rest. Explain to me how that's an object at rest. Okay, we had the cups and we had the paper, and she pulled the paper out. The object at rest stays at rest. What was the object at rest? It was the cups. But did they stay at rest? Are they still hovering where we left them? No. So that means there has to be some sort of unbalanced force acting on them. There has to be an explanation with Newton's laws as to why that motion continues. So let's think about what is the motion or the unbalanced force that's acting on the cups. It's gravity, okay? When I am teaching Newton's laws to the freshmen, they learn that gravity actually has a numerical value to it. It's like saying I drove down the road at 60 miles an hour. Gravity has an acceleration. It's 9.8 meters per second squared. If you want to get ready as an 8th grader to make it up to be a freshman, go ahead and learn 9.8 meters per second squared. Mr. Berg also still knows that. It's a number that just gets stuck in your head. So the gravity is accelerating them downward, but then they continue to stay at rest because of Newton's third law, which we're going to get here in a minute, okay? So Miss Whitney is showing you an object at rest stays at rest. Sorry, I keep doing that. And so The last part of Newton's first law says unless it's acted on by the unbalanced force. In Whitney's demonstration, the unbalanced force was gravity. The demonstration with Brantley, the unbalanced force could be the seatbelt, it could be the wall. It changes the motion. Everything was going forward until the seatbelt stopped the egg from continuing or the wall stopped the car from continuing. So this last example is some of my zebra friends, Paige and Parker. Paige and Parker are going to show you inertia hats, and they're going to show you all three parts together, but remember, look for the unbalanced force.
Hi, my name is Paige. My name is Parker. We are second graders from Ursa Elementary. My teacher is Miss Levers, and my teacher is Miss Mann. These are our inertia hats. An object in rest stays in rest. An object in motion stays in motion.
Okay, so when you see Paige and Parker use their inertia hats, go ahead and skip to the next slide, you're going to notice that they're just balanced on their head. It is literally just a coat hanger with a couple of, it can be wiffle balls in this case, it can be tennis balls, but they're just setting it on their head. So it's balanced. Newton's law says it's going to stay where it's at unless it's unbalanced. So they're just sitting there. So what was the unbalanced force that happened? There was actually two. The unbalanced force at first was a force, a push or a pull. So the kids took that wiffle ball and pushed it, and then it started to spin around their head, and it should continue to spin until poor Parker, his fell off. What caused it to fall off? An unbalanced force. You could talk about gravity is pulling it off. You can say he moved a little bit. It's kind of hard to do that sitting down, so they do it again here in a minute standing up so that you can see it. So there's two different ways to use an inertia hat. But the first one here with Paige, she's going to show you how long these things will continue to spin. Okay, there might be a little bit of friction with her hair. I know Mr. Harshfield talked about friction briefly. Friction is just the resistance to flow. And then Parker is going to do something a little bit different here with his inertia hat. So this is an object in motion stays in motion. Now Parker is going to, watch him. Boom, okay? Parker can spin underneath that thing without it moving. It is not moving because there's no unbalanced force. He's very balanced. He takes that turn all the way around and gets it to stay where it's at. So those are all examples of inertia, the tendency to resist change. And I tell kids, if you just want to know the last two words, I feel like you know what inertia is. It's a resistance to change. Do what you're doing and keep doing it until something stops you. And in Newton's laws, it's an unbalanced force. Okay, so what I'm going to do is show you quickly how to make an inertia hat. So what you're going to do is you're going to take a coat hanger, and I started mine already. I use a pair of pliers, and you want to try and straighten it. Well, I'm not doing so hot right now. Straighten it out as much as you possibly can. It doesn't have to be perfect. And you work on it a little bit, especially at the ends. You can see like where it was twisted at the top. I'm not really worried about that too much, but I got hooked in the microphone, so I'm a little worried about that. And then you're going to straighten it out some more. As I was informed earlier, I talk really fast when I'm nervous, so I'm going to try and slow this down just a little bit. Okay, so once you get this inertia hat or the hanger all straightened out as best you can, I'm going quickly, you bend it in half, okay? We want to have a point at the top, and it's going to end up being on the bottom. This is your little fulcrum. And then you flip it upside down, and you're going to bend each side so it kind of has a heart shape to it. And there's a couple different keys to getting this the way you want it. The first part is the attachment for the tennis balls today, or the wiffle balls in the Henderson twins, has to be lower than your fulcrum point here. So I'm going to bend this down just a little bit more. And then you're going to bend the other side. Okay. I just think they're fun. And I think it's a good challenge for people. I not only got videos of the twins, then I got videos of their mom trying it, and then I got videos of their dad trying it. And their dad, if you know him, he is a coach at Claremore, is got a little bit of advantage on the inertia hats here. So, and then all you have to do, I put some holes in these tennis balls ahead of time, is you're going to put them through the tennis ball and just attach it however you want. I thought the wiffle ball was a really good idea because then you didn't have to like damage anything. And when I do this, They should stay. The other thing that's going to happen is you're going to notice, well, in this case, it actually worked out pretty well. Sometimes it'll lean forward or it'll lean backwards. And all you have to do is manipulate this a little bit, bend the arches here a little bit front and back. And it doesn't matter if it's lopsided this way. You just don't want it leaning front or back. Okay, so then I'm going to set it on my head. And hopefully it's going to stay. Keep your chin up. And I just look silly, but that's not unusual. And then you give it a push. And it should spin there. And it should continue to spin until, everyone, unbalanced force. If I tip my head, it's going to fall off the other way. The friction of the air, there's 4 different types of friction. One's called fluid friction, and fluids can be gas or liquid. The fluid friction of the air will slow it down eventually, but that's just I thought that was kind of cool. Little inertia hats. Okay. So, and then Mr. Henderson doesn't have any hair, so he's I'm going to show him, because his wife tells us.
Watch out for the back of the chair. It works good on your head.
Region 3 Golf Coach of the Year, guys. Coach Henderson. All right. So he's very excited. I showed that, I'm sure. Earlier, I learned that you got to see the inertia demonstration with the egg, and we'll just talk about it briefly. I can repeat it, but I'm doing the same thing that Mr. Harshfield did. What happens here is should I go ahead and repeat it? I'll just show it really quickly as a demo. Okay. So what you're going to do is you have a cup. And I used a plastic egg because I'm a baby and I don't want to break eggs. Set a plate on there, put a tube on top, and then set your egg on top. And you want to try and have the tube over top of the cup. So what happened earlier with Coach Mr. Harshfield? He pulls the plate, and if I do this well, the egg falls down. Okay, this kind of looks like Whitney's demonstration, but for some reason, the tube didn't fall down. Why did the tube not fall down? Why did it not fall in there? And you can get it to do that, but you have to modify this plate. The plate is the problem. So with my paper plate, there's a little lip on the side. The unbalanced force is it bends it. It's a pull on the tube. And so the egg falls down, but the tube is affected. If you just used a 3x5 card, you could get the tube and the egg to go ahead and fall into the cup. But that's just another example of inertia. The egg's inertia straight down into the cup. All right, Newton's second law. There are other laws. The first one's just my favorite because you can do lots of demos. For Newton's second law, oh, wow, red does not work in here, I've just learned. It's okay. So force is equal to mass times acceleration, and all this says is big objects, meaning they have more mass, not necessarily volume, but more mass, require more force to move with the same acceleration. So the really good examples are the bowling ball versus a ping pong ball. If I give them the same push, the same force, then one should move with a little bit more ease. It should accelerate more. And what I usually tell students to do, draw a line right through this equation. Okay, we have force on one side and mass and acceleration on the other side. If I take two objects that are the same mass, let's take two tennis balls, for example, and I want them to have different accelerations. If I want the increase on this side of my equal sign, I have to increase this side. So if I want a tennis ball to accelerate, I have to give it more force, okay? Opposite of that is if I want it to decelerate. Deceleration is just a negative acceleration. We're slowing it down. Or just have less acceleration. This number has to be smaller. So that means I'm going to use less force to push on it. Okay, so examples of like me trying to move things. If it's smaller, there's going to be an easier amount of, or it's easier to push this. There's going to be less force required than if it's larger to get it to go with the same acceleration. Okay, Newton's third law says that for every action, there's an equal but opposite reaction, okay? And Mr. Harshfield mentioned this. He talked about the rockets. And when a rocket is launching, there's an action-reaction force that's occurring. There's fuel that's burning and heating the air below it, and it pushes. The action is actually the push down. The reaction is the push up. Push and pull. They're going to be a force. So we see this action down and reaction back forward, up. We have the balloons. Mr. Harshfield showed us how that can work. Another demo that you can do with action-reaction in the balloon is just to kind of show that the balloon can be a rocket as well. And so what I did is I took a balloon and I inflated it, and then I made a mess on the table, it looks like. And I'm going to tape a straw to my balloon. And through the tape, before I started, I stuck a piece of fishing line. That is a easy object to come by at my house. Hiya. Okay, so I think I'm okay. Well, we'll find out here in a minute. All right. So, and again, take my straw with fishing line through it, tape it to the top of my balloon. See if I can tape it the right direction because I want it to go that way. All right. And then the other thing I tried to do was I added some flour into the end of this balloon. It's not tied shut, it's just clamped shut. And I hoped that, good news, it works. When you let the air out, that you would see the flour move so you can see the action versus the reaction. Let's try that again. If ever there was a time to make a mess, it is science class. Just enjoy it. All right, so I don't know if you'll be able to see this or not. Yes, Mr. Berg. Oh, okay. So I'm going to let this go, and maybe you'll see the cloud of dust come out. Which way is it going to go? Okay. The dust is going to shoot at me. The balloon goes the opposite direction. Reaction. All right. So we've got 3 minutes left. I'm going to recap this, and I'm going to give you some examples of some Earth Day activities that my students did this week. First, Newton's 3 laws. Number 1, object in motion stays in motion. Thank you, Brantley. Object at rest stays at rest. Thank you, Miss Whitney. Unless acted on by an unbalanced force. Thank you, Paige and Parker. Okay, all of those are examples of Newton's first law. So when you get to be a freshman and you have to come up with examples of these, you already know what to do because these kids helped you out. Thank you all, Rogers County. Number 2, acceleration of an object depends on the mass and the force. So if it has more mass, you can affect the force. If it has more force, the acceleration will be affected. And then finally, for every action, there's an equal but opposite reaction. I always tell kids at the beginning of Newton's laws, when I get to the 3rd law, if I'm leaning on the wall, technically the wall is leaning back on me. Okay, action, reaction. I'm leaning on it, it's leaning back on me. Okay, so what I'm going to do was just talk a little bit about Earth Day. Earth Day was a little bit different this year. The hashtag that a lot of people were using as science teachers or just community members was Earth Day at Home. And so I challenged my students to 3 different things this week. The first one was I sent them this cartoon out of the Philadelphia Inquirer. The Philadelphia Inquirer posted this on Sunday just to get people talking and thinking. And their job was to write 100 words and tell me what the author was trying to tell the world. It says we've got less industrial pollution, there's less air pollution from cars, noise pollution at airports, litter on the streets, and all it took was a global pandemic to shut it down. I think probably a lot of people have seen like wildlife articles on the news and how they're coming into urban areas. There was a big article about how the sea turtle hatchings this year are just way above anything we've seen in a long time because the beaches are uninhabited. There's a lot of positives that come out of it. Some of the things my students mentioned was, why are they only picking on the United States? Because this is a global issue. Number 2, some of the things that they talked about were the sarcasm that goes into that, and sometimes sarcasm is effective in just making a point. You don't have to agree with it, but it was just, what is he trying to point out? And I think the idea is if we could just be a little bit more conscious. This is like a whole pause for the planet. What can we do differently? Okay, a lot of people may go back to living their normal lives, and there's so many great things that we'll be able to do. I'm excited to get back to church. I'm excited to see my students again in the fall. But there's a lot of things that maybe we just need to think about changing and what's bettering for all of us, okay? I have a really big issue with global warming. I'm not going to get into it too much, but I worry about the fact that they say like polar bears will be extinct within my lifetime and what future generations and what that's going to do for a lot of the ripple down effect in biology. We could talk about that as well. So then the second activity that they had to do for me was an action activity. And they became fairly clever. There was 4 different options for them. So I'm going to show you some of the options they all had. Option number 1 was protect the planet. Haley said I could share this with you. Her analysis just said for for my Earth Day activity, I went and picked up trash on the side of the road. I went by my house, and there was surprisingly a lot of trash. Not only was there trash, but a lot of glass and can bottles. All of these things are now in places they belong, like the trash. Right now, recycling is not really an option because they've shut down recycling areas, but she has cleaned up her environment for the planet. Yes, sir. Okay, one more. Haley and Hannah are sisters. I have both of them in class. They rode their bikes to the lake. I told them they could run for clean air. It's a big marathon that they have in Philly, but they could walk or they could ride their bikes. So they knocked out 2. They went ahead and rode their bikes to Claremore Lake instead of driving. And it said there's a lot more trash than we expected, which is sad because it's pretty out there. There was enough for us to fill this whole bag we brought. They didn't expect to find that much. And the final one I have here was that they were allowed to draw or create an artistic option. It just says #nature is beautiful. So Lynn's is creating a poster to mention that it was the 50th anniversary of Earth Day, as well as just you can be helpful at home. So many different options out there. I hope that you think about some changes that you could make that could better our planet. Guys, thank you so much. Have a great week, and I'll see you next Thursday.